really make AS route like a single node with the policy that it says it has. Current possible approaches for these problems is first to sacrifice correctness for flexibility. Okay, I have to explain what I mean here. Correctness means you realize your policies correctly. Flexibility means you want to have all the functionalities you want. And the practice today is you want to use MAD, you want to have all the attributes, communities, and everything. But even though you don't get them completely correct. And the second way is you can sacrifice flexibility for correctness. You can identify which policies cause trouble and disable them. It's probably not an attractive solution to almost everybody today. And the third possibility is actually there's a way to achieve both, but it's expensive. You need to have more routers than you have today. And I will explain these in detail. And here's our contribution. We came up with atomic routing theory. This is one of the only 2 slides about the theory. It's a mathematical model to model policies and what does it mean to realize a policy correctly. It is a theoretical framework for exploring trade-offs. We can look at the trade-off between flexibility and correctness, and also if you want to achieve both flexibility and correctness, what's the cost? And the application for it is to derive minimum requirements for realizing policies. So basically, how do I know actually the second and third approaches achieve correctness? It's because we can show by atomic routing theory. And our proposal goes just a little further. Our proposal to you here is something called atomic BGP. It can achieve both flexibility and correctness efficiently at low cost, meaning, and would require only very minor changes to the router. We need to modify the decision process slightly and change the IBGP route dissemination slightly. Okay, that's enough introduction. Let's go to example 1. Here's the 3 conflicting policies. First, so I'm the provider in the middle, and I have 2 customers. One of them has 2 links, and I can reach destination D through both of them. The paths are equally good. I want to allow my customer 2 to use MAD to specify which route it prefers to use. And at router A, I learned 2 routes, so I use router ID typebreak, and I choose the black route. It has a better router ID. And router B will implement hot potato routing. It sees the black route, route 1, and the red route. And the red one is close to itself. If it chooses the black one, it has to carry the traffic to router A and then exit. So router B is going to pick route 3, the red one, which has a MAD number of 1, and the green route, which has a more preferred MAD number, is not used. So my customer may realize this and be angry at me, saying my MAD is ignored by you. What's going on? The keynote talk, they're like, "What are you doing?" So this is a problem. But actually, MAD causes more problems. I'm not going to go into the detail, but MAD-induced routing oscillation has happened in the real world. I can show you how it happened if you are interested after the talk. So how can we fix this? The first possibility, we disallow MAD, meaning we sacrifice the flexibility of the protocol. But I may lose customer 2, so this is not a good solution. That's why we don't do it today. Second one is here, we add a router C and terminate the green and the black routes on different routers. Now, since I have full mesh IBGP inside, all the routers can potentially see all the routes, and they will choose the routes correctly. But this is costly and may not be possible if you are constrained by power. in the data centers. And our proposal is to say that router A really should tell router B both routes, right? And if router B knows both routes, it will not pick the red route. I mean, it knows all three routes. And we call this atomic BGP. I will talk more about it later. Okay, let's go to example 2. It's slightly more complicated. Now there are a few more ASs. I'm still the AS in the middle. Oh, by the way, I think I forgot to mention, orange circles are routers and the white circles are ASs in this talk. Oh, and there's a link at the bottom to a NANOG discussion that about a problem that's related to this example, but not exactly the same one. If you're interested, you can look up after the talk. So I'm again the AS in the middle, and I don't want to provide transit between peers. So even though I learned 2 routes, and the peer route is a little shorter, I'm not going to tell my peer about it. I'll give it a red route, which I learned through my customer. Okay, that's, that's reasonable. And actually, in this case, everybody's happy and traffic flows like that from peer 2 to the destination D. And, but if I get another customer connected, I see, and it's a premium customer who is willing to pay more for the best route I have. So, so I'm going to give it the best route out of the peer and customer routes that I have, which means router C will pick the green route, the better one, and give it to customer 2. But it's a peer route, so I can't give it to my peer, to my other peer connected at the same router, so it'll be filtered. Now I have violated the third bullet, which is export full customer routes to peer. Even though I have the red route, I'm not letting my peer know about it. And why is it and the peer will be angry because it cannot reach D anymore. So why is this a problem? It's a problem because if peer 2 gets a packet destined to D, it doesn't know where to forward it if it doesn't learn another route to D. So it's going to drop it. So we have created a black hole here out of all the goodness of our heart. We didn't try to do this, right? And D will actually eventually realize I have lost a lot of connections. If it's a online shop run by mom and pop, it's going to say, I just lost my users, so nobody's happy here. How do we solve the problem? First, we don't provide a premium service that customer 2 demands. We just give it the red route, even though it's worse. We may lose customer 2, so we don't want to do that. Second, we can add a router and host peers and customers separately. Now we can export the green route to the customer and the red route to the peer. But you need an extra router and the space and power, etc. And our proposal says that you can use the same topology, but just export 2 different routes to 2 neighbors. I mean, what's preventing us from doing that? So this is atomic BGP. Okay, so let's show the examples of how atomic BGP looks like. So now let's just talk a little bit more about the theory. The name atomic comes from the definition, our definition that an AS is atomic if it realizes all its policies. I mean, when it does this, then we can look at it as a single node, like a policy atom. So that's what atomic means. But just to realize all the policies is not hard at all. You can just disseminate all the routes within your AS. Suppose IBGP allows you to do that. Then you can realize any policies. Like you can, for example, you can have combinatorial policies like, I'm going to export 2 routes to this peer, and that's it. No more routes. You can do something like that. It's not clear why you want to do it, but you can. It's essentially like a centralized routing. Every router has all the information. But of course, the overhead is extremely high here. The overhead is measured in terms of the number of routes disseminated in your AS. So it sits in the upper right corner. And the theory actually tells us there's a trade-off between the flexibility in the policy you can have and the dissemination overhead. The curve looks something like this. It's basically telling you that to achieve a flexibility, a certain flexibility on the y-axis, there's a minimum amount of overhead you have to pay. If you can pay more than that, but there's a minimum. And within the shaded region, you can have atomic routing, meaning realizing all your policies. And BGP today disseminates only one route within the AS per session. So it sits at the bottom of this curve because it has the minimum overhead. It can realize policies with strict ranking. If you know what that means, it basically means no MAD. And to think of it, when BGP was first invented, it didn't have MAD. So BGP was a really well-designed protocol. But the problem is, as time goes, people wanted more flexibility in BGP, which is very understandable because it's a business, right? So we bumped it up in the y direction without moving it to the right-hand side. So it's operating outside of the region, and that's why it cannot realize all the policies you want today. And atomic BGP moves it back to the curve by just increasing the overhead a little bit. Okay, so just to recap, atomic BGP, in terms of flexibility, it can realize all policies based on comparing route attributes. I mean, the theory actually allows us to go through the whole curve, but we picked this point because then we can support all today's common policies correctly, including MAD, and any new policies in the future that's based on attributes. We can do that as well. In terms of implementation, this is the most important slide, which I need your help on. Let's do it a little slower. So you need to do three things to have atomic BGP. The first thing is easy. We need to allow a router to select routes for each neighbor independently, meaning different links will export different routes to different neighbors. And this basically means you need separate route selection process for each neighbor class. You can group your neighbors into classes, such as customers, peers, and providers, so you really only need 3 route selection processes in your router. And this is actually, you need separate forwarding table for each neighbor class, which can be done by connecting your neighbor class, one neighbor class to a line card, and just have different forwarding tables on each line card. This is already solved. VRF, virtual routing and forwarding, which is used for VPN, can do this already. But the next change we need to make is, in order to fix the MAD problem, is not available yet, but hopefully soon. So we need to allow dissemination of more than one route within the AS. This is only for iBGP. So to your neighbor, you can still advertise just one route. But within, you want a little more because you want to have enough information for the routers to make the right decision. I will actually, so you need to disseminate at least one route from each neighbor that uses MAD. And if you have no neighbor that uses MAD, then you disseminate one route. So you can see that it's very rare you actually need to disseminate more than one route. The increase in overhead is, I estimate to be about 10 to 20%. So it's really not much in terms of the traffic increase overhead. But the mechanism that can achieve this is not available yet. But the new add path feature to BGP, I think, is being implemented right now or very soon. And that's why I need to, if you think this is a good idea, you should help me and go to Cisco and Juniper and tell them when you design your add path feature, make sure it works with atomic BGP. And that's a very easy way to disseminate multiple routes in a single session. And the third change we need to make is we need to, once the control plane, the BGP decides all the routes, we need to make sure the AS actually forwards traffic along the routes. So a simplest way to achieve this is use tunneling from ingress link to egress link of the AS. You don't need to use anything fancy. IP over IP tunneling is good enough. And these three changes, the atomic routing theory shows that these three changes are necessary and sufficient. Necessary means if you do anything less, then you may not realize all your policies that you want to, or you may, or you may have to pay the price of having extra routers. And sufficient means we prove as long as you do this, you can realize all your policies today. So that's all good. And to summarize, atomic BGP has many advantages. First, it can implement your policy, any policy correctly, and actually it has this added benefit of simpler configuration. Because now policies are defined in terms of ASs and not in terms of individual routers. So what you need to do is to define AS-wide policy, similar like before. And then there can be some automatic tool to generate the configuration for each router, and you just configure each router with the policy of the AS. So I say it's simpler because now all the routers can be pretty much configured the same way. And there's no restriction on the physical topology. So for those of you who know what I'm talking about, for route reflectors to work well, you have to place them closer to the clients, right? So you need actually a lot of route reflectors. But if you have atomic BGP, you don't need to do that at all. You don't need restrictions on the distance of route reflectors. Okay, and I said minimum protocol overhead because we proved that this is the minimum needed in order to achieve the policies. And so the increase is in the dissemination of routes within the AS, which I mentioned to be about 10 to 20%. And the storage of routing tables increases by the same amount. Atomic BGP can be incrementally deployed. It requires only modest changes to the routers. It's really that one feature that we need. And the changes and benefits are local to a single AS. I mean, both the changes and the benefits are local. If you do this, you realize your policy correctly, you don't violate anything, and it doesn't matter what your neighbors do. And in fact, you can deploy it gradually within your own AS as well. For example, you can identify the routers with a lot of connections, which are the key points, and you can deploy atomic BGP first on those routers. And the more you deploy, the more benefit you can get. So correctness here is not a binary thing. And that concludes my talk. I'm ready for questions.
Hi, Greg Maxwell from Juniper Networks. And in your research, you've proven that the changes are the minimum necessary to achieve the policy controls available on a single node. But did you consider perhaps relaxing some of the policy constraints and find out if there would be a much lower minimum requirement? And the reason I ask this is because not all of the policy constraints are of equal importance. So for example, the lowest ID criteria is unimportant or less important to most networks. And if that one is relaxed, then I think the requirements are substantially reduced.
You mean the lowest router ID?
Correct.
So that's a very good question. Actually, I try to downplay router ID a little bit because if you have any tie breaking, you can have the situation in example 1 where, where you have to choose one route out of the two that you have. And you have a chance of, no matter what tie breaking scheme you have, as long as you choose only one route, you have a chance of missing the one that's important. So here, it really doesn't matter whether you use router ID or anything else to break the route. What we need is that you really have to disseminate those two routes.
In order to get the exact policy?
In order to get MAD working correctly. I mean, the main thing that's breaking here is multi-exit discriminator, right, because it's compared only amongst routes from the same AS and not over all the routes. But all the other attributes are compared among the routes from, among all the routes. And because of this, you have to. if you want to get it right.
I still think it would be interesting to see the continuum of compromise between different levels of difficulty and different levels of policy control, instead of seeing complete control versus what we have today. But thank you.
Yeah, I mean, that's what the theory allows us to do, but this is actually really it's a tiny, teeny step from today's BGP. If you want to do more, if you want more policies, you'll have to do more overhead, actually. I'm only asking, a 20% increase. It's not that much.
Right. Thanks.
Well, how do you deal with root reflectors in your ES? I mean, you partly try to disseminate roots inside your ES in the ways they should be disseminated, and I'm sure you know that because of root reflectors, some ESBers are just not aware of the paths they would have used if there had been a real full mesh in the ES. So does Atomic BGP deal with root reflectors topologies?
Does this deal with route of reflector topologies? So, so first of all, full mesh IBGP is not enough. Even if you don't have route reflectors, I mean, in my both examples, I don't have route reflectors. It just takes too long to explain. You will have this MAD problem, even without route reflectors, right? But with route reflectors, you have more problems. So actually, the oscillation, in order to generate oscillation, you have to have route reflectors. So it causes more problems, but this atomic BGP will solve all that. It basically eliminates all MAD problems if you just disseminate that 10 or 20% routes more. And actually the benefit, there are many benefits, right? Your customer will be happy, et cetera, no oscillations. But a benefit is you can use fewer route reflectors. You don't need them to be closer to your clients anymore. So yeah, so I think that's nice, because I heard usually the ratio is like for every 2 router, you have 1 route reflector or something like that. And correct me if I'm wrong, but that just seems insane.
Okay, thank you.
Okay, any other questions? Okay, thank you very much.